We are live.
Hey everyone, welcome back to another Wolfram Institute Life Science stream. We're continuing our conversation today with Carlos and the research that he's been doing. Today, we're going to discuss a few technical aspects of motif detection in hypergraphs, which we'll ultimately be using to design or define a new complexity measure that can capture the degree of computational work that's done in each step of a hypergraph rewrite, which will be important and useful for comparing different rewrite systems that we ultimately convert to hypergraph rewrite systems so that we can actually compare the differences between them. That's kind of a kind of a rough summary. So I think Carlos, maybe you can see that there are two Carloses.
Yeah,
One
one
of
of them
one of
is
those
going to share.
one of those is a tablet, and I think so. Carlos is going to give a something of a kind of a formal, or I don't know, informal, but something of like a kind of a technical um, summary of his views on this. So please, Carlos,
Yep.
go
So
ahead.
let me share my Blackboard. Right. Let me hide this very annoying panel. And here. Okay. And then writing mode. So yes, so basically what I want to present today is a summary of, or an overview, I guess, of what we are going to do with a lot of the functionality that we are developing. So behind the scenes, Nick is doing some fantastic work developing some hypergraph visualization functions and some general hypergraph functionality in Wolfram language. And I hope that this discussion can help Nick see what I'm kind of thinking that the applications will be, at least in the formal directions, right? In more formal context. So you will see that the main object here are going to be labeled hypergraphs. So we're going to be working with labeled hypergraphs, and we're going to be doing motif rewriting, and we're going to encounter algebras out of this particular system of doing rewritings, and then we're gonna see some properties of these algebras in connection to some properties of the rewriting. So to set the stage, first of all, so set the stage. We want to consider our states for the rewriting, which are labeled hypergraphs. So these are things of the kind, some kind of skeleton hypergraphs can look something like this. Maybe this is filled, whatever.
Mhm.
Maybe something around here. Sorry, maybe, yeah, something like that. And then on top of this, we're going to add some labeling. And for the sake of
Mhm.
concreteness, I'll just label the vertices instead of but technically, both vertices and edges are going to be labeled.
Mhm.
So you could do some A, B, C, D, E, F, or whatever, right?
Mhm.
Maybe, okay, let's go all the way, F, G, H, or whatever, right? So everything is labeled. So basically, the main idea behind this is that we want to somehow abstract what happens in standard matrix algebra of
Mhm.
graph rewrites, right? So in matrix algebra, you know that people like to rewrite. Maybe that's a bit of an unfortunate word to use here, but they like to sort of rephrase and re-express the language of graph adjacency as matrix algebra, and they would like to. Some people like to, if given a matrix ij, they want to express graphically what that represents. So often they would draw something that looks like this. Maybe they label also the edge with an A. So now so you make this jump from, instead of representing every single edge as part of the data for your matrix, your entire matrix actually becomes an edge in a graph of indices, right? So now your vertices are indices and your edges are the entire graph. So in this kind of approach, you end up with categories, right? So that's kind of where you're led into categories. If you think that your vertices are sets and your edges are relations, you think if your vertices are vector spaces, your edges are linear maps, etc., right? So this is kind of how you get into a categorical treatment of this sort of compositional objects.
I see. Okay.
Now the main thing is when you multiply the algebraic operation that you have on, say, defined on matrices or relations, normally we'd write something like this, right? So we sum over P, some index P that is common between A and B, and we have something like this, right? So if we just write the diagram, and this is going to look very familiar to a lot of our viewers from last week, we're going to write something like this: A, B, and then I, J, and then P in the middle, right? And so we're effectively summing over this P, and the result of this is, okay, so if I call this C, I, J, the result of this is going to be C, right? So it's going to be something that lives, it's a bit too exaggerated, lives between I and J, and P is still there, just left alone. And then, so there's C, right? So you can, obviously the operation has some, linear combination of the indices, of the values along the indices and so on, but you can effectively capture it as a rewrite rule, right? If you notice, this box here is just a rewrite rule. It has exactly the information of a rewrite rule. And that's kind of the starting point of this entire business, right? That we can express compositionality of these objects, which we can think of matrices, but obviously there are general morphisms in categories, and there are many other things, as we shall see if we have time to discuss, that can be expressed in this graphical way. And then the compositions and the operations that we perform with them are basically just expressed in terms of rewrite rules, right? So this is kind of a dual perspective from what we had last time, which is last time we express graphs and we look at their adjacency matrices, and then we look at an adjacency condition within those graphs, and we notice that the operation itself gives you the rewriting that happens kind of locally in each collection of vertices. But this is kind of an abstraction of that phenomenon. It's not really a duality. It's more like an abstraction where you're saying, I'm gonna take my generic index I to represent a generic vertex in my graph, so to speak. Yeah. And then you take your generic vertex P and generic vertex J, and then you make this into a diagram. And basically you abstract the construction as a diagram. And then the diagram does become a graph that lives kind of on top of this actual graph. If these are adjacency matrices of actual graphs, which they need not be, but if they are, this is kind of a graph that represents the graph rewriting on top, right? So it's kind of that level of abstraction. But you can actually do this without any reference to graph rewrite, to graph adjacency, to begin with, right?
Okay.
So what's interesting, to remain in familiar territory for the moment, what's interesting about this approach is that one important aspect of the left-hand side here, or the sort of algebra or matrix composition side of the story, is that this is a non-commutative product, so you want to be able to do something with this product that is kind of operational, and for that you need some kind of properties, right, to manipulate. And of course, you know that this is the operation that comes from distribution with the sum and multiplication. There's no problem. But if this is the primitive operation, like morphism composition in categories, then you need some kind of property to actually manipulate them. And so we all know that this product has associativity, BC equals ABC, right? Meaning that you can essentially just write this as ABC, and it's unambiguous, right? So, so this is an algebraic fact. This just comes down to the fact that, well, your field operation or your semi-group operation, semi-ring operation is distributive, right? And you have associativity for multiplication and addition, and you have distributivity, and that's basically what you need to use to show that property. But what's interesting is that this actually has a direct manifestation in the graph side, right? In the diagram side. I prefer to call these diagrams instead of graphs, so that we don't mix the graph adjacency stuff. So in the diagram side, we can write this, right? So what is ABC? So ABC is the situation where you have. So if you were to write, okay, let's write this formula, right? A times B C. So this is a formula that, just follow. You first do sum over P of AIP, and then you write another formula here, which is going to have, first index P and then another index J, or let's say K, but that is itself B times C. So that's going to be sum over Q of B, and that's going to be first index, which should be P, and then sum over Q, and then final index, let's say J, for example, right? Let me call it more conveniently. No, actually J is fine. So this formula, you can distribute everything, and you find that this is just sum over P and Q of ABC, right? With the right indices, AP, PQ, QJ. That's not important, there's some mess there. The point is that it's one single value, and it evaluates to the same thing when we have the other way around, A, B, and C. So the point is, if we represent the diagram for this with this rule, right? And anytime you find the product of this kind, you draw a diagram of this form, then the diagram that you have looks indistinguishable in both cases. That's why they're both evaluated to the same thing, which is this diagram, right? You do A, B, C, right? And these indices are P, Q, and J. That's the diagram that you find when you write either of two. And so you might be thinking, but I don't see the brackets. Why do I have brackets in the expression and not in the diagram? Well, that's because, that's kind of the power of diagrams, right? The diagrams have some natural structure in them. And so the idea is that if you have to change your mindset that we're not doing algebraic operations, we're doing rewrites, which is kind of a different way of operating, right? At this level. So we're doing this rewrite, this boxed rewrite up here. And so what that means is that I need to apply that particular rule to this diagram. So everyone sees that I can apply it in two positions. So maybe I will highlight something like this. So I highlight this position and I highlight this position. Oops. And so I continue. So this is that position and this is that position. And so this gets rewritten in two different ways. The first one obviously takes AB, and so it gives me this kind of diagram, QJ, CI, and this is now AB. This one here gives me IP for A and J for BC, right? And so the crucial point is that now they both rewrite to something that lives between I and J. That's kind of the key point, I and J. So you have these two edges here. So this one is A, B, C, and this one is A, B, C, right? So in terms of just the diagrams themselves, right, you end up with a confluent diagram, right? Because in both cases, you have a single edge between I and J, right? So as a diagram, it looks indistinguishable. It's the labeling of the diagram that gives you some non-trivial information, right? And it's precisely this idea that you started from a simple diagram, simple in the graph sense, right? It doesn't have any multiplicities, and you ended up with multiple edges on the same edge side, right? So that's how you can characterize associativity. So associativity is tantamount to basically, so ASOC is basically in the context of rewrite is confluence on the one hand, because we have confluence,
Yes.
but on the other, it's not just confluence, but it's confluence of a rewrite system that had overlaps, right? I mean, it's crucial that this this particular edge here, I'm going to highlight in blue. That edge over there is shared among both motifs, right? So I haven't introduced the word motif. I'm just talking about this particular shape because this is the motivating example. But that's basically the idea. The idea is that you have this pattern that you had overlap, and so associativity tantamount to confluence plus overlap.
Okay.
Right.
Yes.
So
Yes.
this gives a very compelling kind of primer to say, well, if this is what, so by the way, this is how you prove, not prove, but this is how you many times teach associativity in category theory, the associativity axiom of a category. I mean, if you're in a category, you write something that like this, right? Some morphism like this, right? FGH. The kind of the shorthand way of saying what is the axiom of associativity is to say that in this sequence of morphisms you can compose in two possible ways. You can compose FG first and then H, in which case you get this morphism, or you can compose GH first and then F, and then in which case you get this morphism, right? So F composed with GH, or FG composed with H, right? And the axiom of associativity tells you that those are one and the same, right? They have to be the same. So we're kind of rediscovering the wheel here. It's just kind of nothing too fancy. But the crucial point is that category theory doesn't rely on rewrite, right? They don't explicitly rely on rewrites as a formal system. They axiomatize. They say you have set or a class of objects, and you have hum sets and all this kind of business, right? So the key idea here is if you want to generalize the notion of algebra that might be necessary for the treatment of say spectral theory of hypergraphs, because you want entropy at the end of the day, right? Like we never lose sight of our objective. It might be that the treatment of algebra is actually is insufficient when just dealing with the usual compositionality of algebra, right? Meaning that if you just write things down in some kind of composition of A and B and C, that might not give you the full picture. The reason being that what happens when you have higher compositionality, right? So this is binary, and it's binary because you're essentially doing this adjacency that is kind of stepwise. Right, you're doing path-like adjacency, and that's why everything boils down to a chain, which is to say, very old result that algebra, monoids and groups and all these kinds of things essentially boil down to string rewriting. Right, it's that kind of moral of the story in the background. But obviously, we can do many more things than chains. That's something that looks like a sequence. And then you discover other things, right? So before you go there, someone might not be convinced that this is any good, and this is just rediscovering the wheel, it's just doing categories again, it's nothing new.
No. I see where you're going with this. Yeah.
So the interesting thing is you say this is associativity. Okay, I didn't learn anything new. This is exactly what I know. It's a commutative diagram. Blah blah blah. This is very familiar. However, there is, for example, I'm sure that a lot of people have not thought of so this is the axiom of associativity. Okay, cool. This is one half of a definition of a category, associativity. The other half of a definition of a category are units, right? And once you have your morphisms and your objects, you have the unit axiom and the associativity axiom. Okay, so let's think for a moment what it means to have units, right? What it means is that if you give me one way to, I guess, express having units means is that you have an object, A, and this, take it as a diagram. You can always write the following diagram, right? So A to A, right? Again, not typically presented as a rewrite rule, but very clearly phrased as a rewrite rule, right? And of course, this is going to be labeled by something that remembers the object A. So you call it A1A or whatever, right? Okay, but that's not enough to have a unit. I mean, yes, part of the definition of unit is that there exists one for each object, right? At least one. But what you actually want is to say that they behave like neutral elements, right? Like the units are like the neutral elements in groups, right? Like these are the do-nothing morphism, right? Okay, so if I have the composition, the composition of morphisms encoded with this rewrite rule, right, as we just said, and we know it's associative, I mean, it behaves in this particular way. Let's see what happens when I consider a morphism, right? So let's consider this initial state. Take AB, so again, it's going to be like a labeled hyper brackets graph, F, right? This is some initial state. And now imagine that you have the two rewrite rules, right? Unit and composition. So obviously we cannot apply composition because there's nothing to compose. Our matching of our pattern doesn't work, right? Because we need to find two morphisms in concatenation. But we can apply unit to find something that already looks like that. So let me duplicate A, for example. So A, B. Right? So I duplicated A, I get B, and I have a new state. This is now 1A. Okay, fine. Now I can apply my composition rule. Sure. So I apply my composition rule, and then I get a morphism from A to B, which I call one compose F, right? So I call it A, B, and I call it one compose F, for example, right? And so this is a new state. Now, technically, I'm always doing these additive rewritings, right? Like I'm always throwing the stuff on top, like I did here in the previous diagram, right? So I find something that's multiple from a simple one. So I should also write the fact that there's F here. I mean, maybe perhaps I'll just, I'll write both. I'll write there's F, what a mess, sorry. So there's F here, that's how we started, and there's also one compose F. So we have we started from a simple diagram. We ended up with a non-simple diagram, and so in precisely the same way as in here, where we confluently arrived at a diagram that has the same sort of edge type, so to speak. So it's a edge AB in the same way that this was an edge IJ in this previous example. Then you say, well, I just have two labels that have different names. One is F, because it was the original label, and the other is the one that actually comes from rewriting it. It carries some extra information. So this same principle will tell you that no, actually they are the same. This non-multiplicity principle tells you that they are the same. And them being the same is precisely the axiom of units. Well, in this case, left unit or whatever. You do it for B, you get right unit. And same idea. And from this, you can actually prove that they are unique, and same idea, right? So anyway, this is kind of a slogan or kind of marketing piece to advertise that it is actually perfectly doable to take a formal system like categories, which, remember, they subsume all things like monoids and groups and all these kinds of things, right? As algebraic compositional systems, right? Not as the categories of those things, but as compositional systems themselves. And so it makes perfect sense to actually go with this rewrite mentality, because we not only have a nice diagrammatic way of thinking about it, which is already useful, but we actually have a formal handle on the axioms of the theory, right? So we can actually use rewriting as a way to formally encode the axioms themselves, like what people would actually call the categories themselves, right? Like what a category is the information of the formal rules that you have to follow. So we can actually do that in purely rewrite language. And this is something that, to my knowledge, has not been done. Like, this is not something that is out in the world that you can read about it easily. It's kind of folklore. A lot of category theorists think in this way, and they will explain things like this, that you find, two morphisms between two objects and they have to be equal and so on. I mean, that's how I learned about this. I mean, that's not my observation. That's how I learned category theory. I mean, people explain that way. But the observation is that, okay, so now when you want to actually generalize, because you have something like a hypergraph that happens to have order 3 edges, then you find other things. By the way, just for the record, I won't go over the details, but for the record, if people are curious, other kind of standard categorical structures that you can prove that in the same way are things like, so for example, when you have something like an involution, something that is sort of an endofunctor that sends morphisms to themselves, and you want it to be nilpotent, something like conjugation in groups or inversion in groups, right? That has usually this property that take the conjugate of the conjugate, you get back to the same thing, right? So that can be encoded with a rewrite rule, which is basically you give me a morphism AB, I give you a morphism star BA, right? That's kind of the rewrite rule. So you can actually show that this property comes from that in a very trivial way, because it's just reversed twice and you end up with two morphisms in the same direction and they have to be equal. But also this other property of like dagger categories, which is the sort of anti-distributivity, I guess you could call it, of dagger categories, where you have, this property, right? This is the usual, dual conjugate kind of property of morphisms. That can also be shown in this way. It's very elegant. You just draw the diagrams and you end up, right, so I could arrive at a morphism between these two objects in this direction with this name, the left one, and I can do the same thing for the right one, and therefore they have to be the same. So it's actually very elegant that you can encode all these algebraic properties. By the way, also operads, which are a bit more complicated because these actually involve higher order stuff. So operads and semi-heaps, semi-heapoids, because they are not close. I mean, it's not a big difference. So these two are actually examples that use higher order stuff. So these are two cases in which this approach actually becomes clarifying. This is not just a reformulation or some kind of exercise in rewrite gymnastics. It's like just doing it for fun, but it actually proves useful to spot a pattern that was not readily realized otherwise. And just to explain the perhaps the most visibly enticing one in the case of semi-heapoids. So semi-heapoids are these structures. I think we've commented on them in some stream for some random reason. I can't remember. But they are basically, so a semi-heapoid is a set with a ternary operation. So this is set S, and this is a ternary operation, right, taking 3 elements. And it satisfies a very specific associativity-like axiom, which reads as follows. A, B, C, D, E. These are generic elements in S. So this is exactly what you would write as associativity when you have 3 elements in your operation, right? You put a product and then that product inside a product, right? So I'm gonna leave the middle one mystery for a second, because the right hand side looks intuitive. You move the bracket associatively as you would A, B, C, D, E. But in the middle, you have a departure from associativity, because you twist D, C, B, E, right? So what's happened is that you put the bracket in the middle, and B and C have swapped. B and D have swapped positions.
Yeah.
Right? Yeah. Okay. This was called. I don't know if Nick can help us with a Russian. I think Gruda or something like that in the 50s by Victor Wagner in Russia and the Soviet Union. I don't know.
What was it called?
What's it again?
Gruda, I think, something like that. Gruda. I can't say the Russian. It sounds very bad, I'm sure. But,
how's it spelled?
I don't know. I mean, that's the phonetic kind of. It was translated as heap, right?
It's kind of Gruda. Yeah.
Right. So anyway, it was given this name. Some people say that because it sounded like groups, but I think that's kind of a bad I think it's more because of the examples that he had in mind, which were maps. He was a differential geometer, and I forget actually where he was. He was the second algebra school that in the Soviet Union. One was in Moscow, the other was in somewhere else. So there, I can't remember where it was. Anyway, so yeah, this is V.V. Wagner heaps. So that's where this axiom was kind of discovered. I mean, it was known before because, by the way, if you were wondering what the hell is this, you can make one of these things. Choose your favorite group, G, with operation dot, and define the following ternary operation. You take A times B inverse times C, right? Because it's associative, you can actually do this without any brackets. So this is a single well-defined ternary operation. And you can imagine that if you put, A, B, and C are where you're going to place your three elements when you do the axiom, right? So if you place it in the first argument, that's just multiplying, so it's just going to be associative. That's why you can move the brackets all the way to the left or all the way to the right. So if you place your triple product inside of A or B, A or C, left or right, you're gonna get the same thing. But if you put it in B, because you have a -1, you get this kind of property, right? You get this involution property, right? And that's why you get D and B flipped in the axiom. Anyway, so these things have been studied. I mean, there's some literature. They're quite mysterious still. There's not a lot that is known about them. In fact, there's some papers still coming out. People working on these structures nowadays. But what's very interesting is that just like categories, just like groups, just like all these structures, you can understand this axiom of because when you look at the axiom, you're like, oh yeah, it looks clearly like it's motivated by something like this, but it can actually be motivated from purely rewrite diagrammatic calculus that is extremely, in my opinion, extremely intuitive, that you never forget, like that you should write that axiom. So there are two ways of doing it. One way is with graphs, and the other way is with, let me say with 2 graphs, and the other way is with 3 graphs. Actually, n graphs, but they're kind of different because this is directed and this is undirected, or can be undirected, I guess. So with directed, the rule is as follows. So you take diagrams of this form. So this is the basic operation, right? This is not. So it's a diagram that is flowing in 2 opposite directions instead of 3 flowing like the associativity one. This is ABC. And this gets rewritten to a single, dot here, dot here, dot here, dot here, a single arrow, call it ABC. Right, so that's one way to do it. And you can see the analogy with this dagger, right? Because A, B, C are just morphisms, and the way you get B to go in the opposite direction is if you have A, B, C all flowing in the same direction and you apply a dagger to B. And because dagger has this anti-distributivity property, then you get the appropriate axiom. So that's quite an intuitive way to see it. But actually, you can do this for n graphs, for undirected n graphs, the lowest version being the ternary one or the order 3 one, which then looks like a fish, and it gives the name this fish stuff. And so the rule is as follows. So you write something that has two different orders of indices, of kind of input-output indices, or left and right indices, or black and white, or whatever. And you write this kind of pattern. So these are now filled edges. So these are 3 edges. Put the white there.
Can we call them hyper edges?
Yeah, hyper edges. Yeah. These are
okay.
Absolutely hyper edges.
Yeah. Okay.
I just say edges for short, but yeah. So And then this gets rewritten to a single triangle between kind of the tail tips and the mouth, so to speak.
Okay.
I mean, it's important to remember that these dots are still here. They didn't go anywhere. It's just a rewrite.
Mm-hmm.
And so, again, if you call this thing, maybe some color is going to help. Purple, maybe. So if you call this that's very dim. So if you call this A, B, C, this is
Mm-hmm.
ABC, right? And basically, the idea is if you want to write this kind of expression A, B, C, D, E, right? You're going to have to kind of attach 5 triangles, right? And so you're going to have something like, I'm not going to write any vertices anymore.
Yeah. Okay.
So you have something like this, A, B, C, D, E, and then you do motif rewriting, right? This is the whole point. By the way, I haven't really introduced motif, but motif is just a way to choosing one model hypergraph. So in our context, it's just choosing, in this case, the left-hand side of our rewrite rule, right? So our motif is a fish, and so you go after the occurrences of fishes in this long fish, so to speak, right?
Okay.
And so you get 3 hits, right? 2 are kind of obvious, but there's a third one as well.
There's a third fish.
There's a third fish. So the first one is
Oh, I see. Yeah. Okay.
in the right.
Yeah.
Sorry, in the left. Here's in the right. But then there's one in the middle.
Yeah. Right. Yeah. Facing the other way. Right.
But it's swimming in the opposite direction. That's the thing.
Yeah. Tuna and salmon. Right.
Yeah. And here's this one and this one. Right. So there's three hits for the fish, and you can probably see where this is going, right? You get then each of these look like fishes. I mean, let me use my color code a bit consistently. So this is here. This is here, and this is here, and the rewritten part is this longer triangle, this longer triangle, and this longer triangle, right? So if I actually keep track of the labels, this is ABC, so ABC go here, DE, this is A. Now, this is BCD in this order, so I'll keep it like that for now, and this is A, B, C, D, E, right? And of course, these are all fishes again, and so they are going to rewrite to a single triangle in the end, right? Now, importantly, let me just write one big triangle in the end. So importantly, notice that the vertices, I didn't draw them, but they are there.
Sure.
Those 3 vertices actually correspond to these 3 vertices, right? So we have the same situation as before. We have 3 different triangles, all written on top of the same 3 vertices. And so the idea is the first one, I'm just gonna draw 3 triangles so you see 3 options. So the left one, you get ABC, that's the bracket, ABC, DE. The right one, you get AB, CDE, that order. Because we are taking the convention that tail, body, head is the sequential order that defines the tuple ABC, right? When you define, this is a choice, right? Like you have a hypergraph and you have to come up with some kind of convention, some kind of, mapping of your elements. And therefore you have to agree that if my head, body, tail happen in the opposite direction, obviously the body still plays the role of the middle. So there's going to be A and E play the role of tail and head. That's right. Now the middle element is a fish that is swimming in the opposite direction. Therefore, I'll have to look at the role of tail, body, and
Oh,
head.
so
So it becomes
is it D
DB,
DB? Aha.
which is exactly the axiom
Yes.
of
Yep.
semi-heaps, right? Or heaps or whatever. Anyway, so it's a long story basically to get convinced that we not only recover this motif rewriting kind of approach not only recovers all the algebraic structures that are very well known, monoids, groups, semi-groups, all these kinds of things, categories, more general semi-categories, all these general things, but also daggers, operads, these more higher compositional structures. But also when you go into this higher arity land that is very unfamiliar, which is, by the way, the natural land that we have to traverse because of this hypergraph spectral theory, you actually can make headway, right? You can understand that this seemingly complicated associativity axiom that was basically has been ignored for the best part of the 20th century for its lack of intuition, lack of good examples, actually not lack of good examples, because every dagger category is an example of these things. And dagger categories are fundamental to a lot of things, quantum mechanics and all kinds of things. But it's very counterintuitive to think of this. Why should you associate things in that complicated way? Well, diagrammatically actually makes a lot of sense. So that's the whole point of this motif approach, and the reason why having all these tools for hypergraphs, motif detection, having the ability to actually write everything as a labeled hypergraph allows you to have this kind of very pristine, sort of minimalistic go at it. So, by the way, if you've ever seen, the most interesting example for me, for the more mathematically minded in the audience, are operads, because these are the ones that are higher order, and these are the ones that most people claim to be the sort of proper way to do higher arity algebra. Algebras over operads are the real thing. What's interesting is that operads basically, for those who don't know, are a generalization of categories in which, or can be seen as a generalization of categories in which your morphisms take this kind of shape. So several objects into one object, right? So this is kind of the one way you can imagine operads are like multi-maps or tensors, for example, right? Or multilinear maps, I guess, right? Like they have multiple arguments and map into a single target, right? And so operads can be composed, as you can imagine, in this kind of way, right? If I have F and G, F is a map from 3 objects to a fourth one. F is 4 to 1, G is 3 to 1. You can compose them in different ways, right? I can put G in 4 different positions, and I can put F in the different positions of G, and so on, right? And so the idea is that operads have some associativity property that tells you that if you do this before or this before, it doesn't really matter. So when you actually write F and G as hypergraphs in this kind of diagram philosophy, you can actually show formally that if you have a rewrite rule that looks just like this, where this is your state and this gets rewritten to something that looks like, F compose G to a single object of, 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. That looks something like that, right? With 6. And everything is being kept track of, order or whatever. If this is your rewrite rule here, then you can actually prove formally that the same property that overlapping confluence is going to give you the required axiom of operad associativity, operad composition associativity, right? So anyway, it's just overwhelming evidence that this motif rewrite approach is kind of it's like a hidden pattern that was not really realized in modern mathematics, and it fits very well with all this narrative of let's make mathematics computational, let's make the whole formal system emulation into a set of rules that can be applied, and you don't really know where you're going unless you already know the answer. Like in categories, you already know that you're going to define categories when you choose units to be rewritten this way and composition to be rewritten this way. And operands, oh yeah, sorry, I was mentioning operands because they have an entire tower, infinite tower of rewrite rules, right? Because every single, each order of the operands needs a different rule. Like, composing something of order 4 and order 15, that's a rule. 15 with 13, another rule, 2 with 3, another rule, right? But they all look the same. They're all basically the rule that you can kind of concatenate them or like splice them in some kind of way, right? Like funnel them in some kind of way. So that's an example already of a theory that is very popular. Operands are extremely popular in algebraic sort of categorical treatments of algebra and things like that are already kind of hinting at this idea of, oh right, yeah, you have your operations there. There's a tower of infinite operations. It's enough as long as we can draw the diagrams. Right? So this is kind of already hinting at this idea that we have the rewrite rules. We don't know exactly what they're gonna do, but they're gonna have natural consequences that can be experimentally captured. Right? And experimentally here just means drawing diagrams. In our case, might mean measuring entropy of different rewrite rules. It might mean drawing diagrams or drawing very big final states of big diagrams and things like that. But it's kind of a nice confluence of research lines that are otherwise quite separate. So anyway, so this is kind of a marketing piece for why motif rewriting is actually super natural in this context of formalizing formal systems, encoding formal systems, that's what I want to say. Encoding formal systems as labeled hypergraphs, which are amenable to complexity measures, which are amenable to embedding motif detection based approaches to spectra and eventually entropy and things like that. So yeah, that's kind of a summary slogan piece. We'd love to hear your thoughts.
Wow. Let me just take that in for a second. First of all, that was a very well delivered talk. So
Thanks.
this is, I mean, the immediate questions that come to mind are somewhat practical, largely how we'll use this for defining motifs in our particular study, but that might not be the first place to start. There might be some more general questions that should be asked first. So I might pass it to Nick before we start talking about the particular research that we've been doing, because this is kind of, as you said, it's kind of a general.
Yeah, these are marketing pieces, not so much super directly following up from the stuff we're doing.
This is kind of higher arity propaganda, basically.
Yeah.
But there might be some general questions first. I'm trying to think of some, but most of my questions are kind of relate to the study at hand. Just because I'm writing up the reports, that's kind of what I'm thinking of. Nick, do you have some general propaganda-related questions?
Well, propaganda-related, I don't think so. But the specter question is kind of still.
Yeah. Okay, so Nick is like me. Yeah. Okay. Right.
Like, how do we go about, and how those motif definitions and rewriting can help us to define spectral properties?
Yeah. No.
Yeah.
Well, I mean,
Yeah.
exactly.
Yeah.
So one of the reasons why I wanted to do a marketing piece on motif detection, motif rewriting, is that okay? So here's the basic line of argument. Maybe I can even graphically express it. So spectral theory is essentially based on algebra, right? So it's effectively a question within algebra. right? You have a particular way of doing algebra with your objects, and you pose the spectral question of like eigenvalues and eigenspaces and things like that, right? So you could just forget that the spectral question, let's put it that way, the spectral problem comes from that algebraic setting, and just look at what it gives you, right? It gives me a set of eigenvalues, it gives me some data that is, some condensed from this eigenpolynomial of my thing, right? I have some other algebraic object that contains some of the information, and it's independent of basis, blah blah blah. In some sense, it's like the proper information of this thing, right? You can abstract it that way and just say keep it like that, and then think, right, that's what I want to generalize, and that's perfectly reasonable. And there is some work done in that direction. People are, well, I should say, people are working on this. Like the people I'm contacting with hypermatrices for the event, many of them are working on exactly this, on polynomials, invariant theory for these higher order matrices and things like that, right? This one thing that you can do. The other thing that you can do, which is more my suggestion here, is look at the fact that we came from a particular algebra. The spectral problem of usual, spectral theory is based on matrix algebra, right? And so my suggestion here is to say, well, if we generalize this algebra, because we know that we have to, it's not that we're doing it for sport, we know that we have to generalize the algebra because that's the natural adjacency algebra that comes from hypergraphs, general hypergraphs, then you have to understand these algebras to be able to even pose the question of what is the spectral problem in this context. Right? That's my entire argument here. My argument is that if we don't have a basic understanding, you don't have to become like the world expert on these algebras and like just lose yourself 20 years doing a study of these algebras to do that. But you need, at least I do, you need this minimal understanding of what is happening algebraically in a general sense to be able to formulate the spectral problem. In the following sense, so one way to understand the spectral problem is to say, if you have something that can be understood as an operation, something like this, you want to ask this kind of question where this is a singled out element of your theory that behaves like identity. So even forget about identity, even forget about the specifics. What you're saying here is you're saying, look, we have a vector space structure, so we have proportionality as kind of the projective relation in your space, and you're basically saying that you want to take some general element of your algebra and you want to make it projective equivalent to another canonically identified element in your algebra. In this case, it's the identity, right? And this is, I think, enough to be generalized to other situations where you're like, okay, if I give you, the fish algebra or the Bhattacharya-Messner algebra or whatever, some of these dagger groupoids or operats and things like that, what are the canonically identified elements in this context? So does it still make sense to talk about vector spaces? Yes, it does, because that's all you do is you define everything over your scalars or whatever, and you have a vector space. So does it still make sense to ask that these things are projective related? Yes, it does. So my first intuition when coming from this more algebraic angle to spectral theory is to say, if I have a motif that induces an algebraic operation, that algebraic operation might have natural identities, or not just identities, but singled out elements that behave in a special way. They are canonically identified, like the identity matrix, right? So then the obvious thing to do, in my opinion, is to say, well, a spectral problem is general object of your theory operating on something equals proportional to something else, right? And that's basically what I would suggest that we do for this spectral theory. Now, the problem is that you end up with something that looks quite bizarre and quite exotic, right? Because if you do whatever the three choices that we had, the cone, the blades, and the 3/4, or you do the fish or whatever, you have this. The ternary identity, but you have these partial identities, and you have all this kind of noise that is kind of more like a rainbow of possibilities more than just identity is a single element. That's it. It's more binary, more sort of like black and white. This is kind of more technicolor algebra kind of situation, and it's a bit debilitating in the sense that it doesn't allow you to just run with some approach, but at the same time, I do have the feeling that the fact that you cannot just run with something, it's actually a good thing. Like it means that you're kind of bashing against some wall of the unknown, right? And you're like, I can go further easily, right? And that's in my opinion a good sign. So to kind of bring back to the worry of like, okay, so how does this help at all with spectral theory?
Yeah.
My suggestion would be that a general treatment of hypergraph. So essentially, my suggestion is forget about algebra. So it can be summarized as forget about algebra. In that, I mean, this is kind of something that I sort of discovered during my sort of RET studies like a few months ago and in the last couple of years. Like, it took me a long time to realize that if I want to actually make progress in these kinds of things, and in this case it's useful for this spectral problem of hypergraphs, complexity, blah, 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 the things that we want to do, I would say you have to forget about algebra. And I think this is where we all really come together in a very sort of a consonant way, because this slogan that I presented today basically tells you that the right way to do it is via rewrite theory, right? It's via computationally driven kind of procedures instead of more axiomatically imposed behavior, right? And that's kind of what I always thought was kind of the perfect marriage between what I was doing in my research before I joined the Institute and what we would do at the Institute. I'm very happy that at some point in the project that we all decided to do, it's actually useful to consider this. But that's kind of the bottom line that I'm trying to claim here, that you don't need algebra at all, right? But we have to. So okay, if you don't have algebra, how do you formulate the spectral problem? Because
right.
And there's where just
is there like basically two ways to, or maybe more, to formulate it here. If you just look at this expression of eigenvalues, right? Your right rules can either be the dot there, which is just doing some rewriting of the hypergraph, two hypergraphs, two other hypergraphs, right? Or it can be the A itself.
Yeah.
And dot would be the application of a rule. So it's like completely two different spectral problems. Either we're studying the spectral theory for rewriting rules, or we're studying the spectral theory of hypergraphs themselves. The things that we are rewriting.
Yeah. That's different. Yeah. I agree. Now, what I was going to with my forget about algebra kind of speech is that when you understand, this is something I mentioned last week actually, and I've been pondering about it. Unfortunately, not much progress being done because honestly, I didn't think much. I didn't progress much in how to interpret it. But I do think it's the right approach, which is to understand that this expression is operating. I mean, typically people say it's a adjacency matrix, and this is in the context of hypergraph, graph theory. It's an adjacency matrix, and then this is some weights distributed over some mass or something distributed over your graph, right? And so applying A to a vector X of masses basically disperses the masses, right? Like it just sends them around. It's like diffuses the masses, right? So you can abstract this and say, okay, if I have my hypergraph mindset, this is just the adjacency. The adjacency hypermatrix of the two graph, and this is the adjacency hypermatrix of a one graph, right? I mean, this can be multiple, so they can be over naturals or rationals or reals or whatever. So this particular operation here, this is just contracting, right? This is A, P, sum over P of XP, right? So it's just one of these particular. So if you looked at the diagram that we drew before, this would look something like this, right? A, and then X in here, where this is, index, let me call it J, and this is I, and this gets rewritten to just something on I. And of course, J is still floating there, right? So this, my entire kind of point today is that the eigenvalue problem perfectly fits this description of rewriting, right? It is this particular way of rewriting, and of course it uses a lot of machinery and linear algebra and all these kinds of things that it's much more sophisticated to say it just reduces to doing matrix operation on a vector. I mean that's stupid, but it is a question of how you operate, how you rewrite in this particular way, right? So I didn't want to just do all this kind of like marketing piece to just say, oh yeah, it's kind of related, interested. No. What I wanted to say is the eigen problem, the spectral problem is actually just one example of this, right? And so what it remains to be done, and this is work that we probably should do at some point, is to know exactly what it means in rewrite language to be proportional, to be all these kind of eigenspace, all these kind of things. And I mean, unfortunately, I haven't really worked with spectral theory a lot in my life. I mean, I did quantum mechanics and I did the usual stuff, but I haven't worked with like numerical linear algebra a lot to be very fluent in all the techniques that go around. But to be honest, that might be better, that I'm not biased to like jump in some kind of methods that people use a lot, right? So anyway, that's kind of my bottom line. So what is your reaction, Nick, to the fact that there's this rewrite rule that captures the kind of flow?
Well,
So
first of all, I think this J that should disappear, right? You only allowed to have a single index on the right. You basically count.
Yeah. So sure, yeah.
So
yeah,
your eigenvalue basically counts the number of empty hyperedges after you do the rewriting.
I mean, yeah. I mean, this doesn't. I mean, this particular rule. Let me highlight it like this. I don't know. This rule is not about eigenvalues, right? That's just matrix multiplication. That's just let's say matrix application on a vector, right?
Yeah, but still, the number of vertices should change, right?
Yeah. I mean, I think this is mostly conventional. Like the fact that I still write the J, it's just a matter of. I mean, you don't destroy. Like you don't destroy the. I mean, if you think you destroy the where X lived, right? It's just a matter of like, if you have this graph, I and J are two vertices of the graph. You have X as some one edge on J, right? You apply A to the one edge, it moves to I. I mean, the vertex J doesn't disappear, right? It's the one edge that disappears. Is this distinction between vertices and one edges that I
don't know. I think of it that when you do the contraction, it's the vertices that disappear, and well, together with the hyperedges, and new hyperedges are being created on top of the new destroyed vertices after you do the contraction.
But that's so. I mean, I'm not saying that's. I mean, this is just conventional. I don't want to say that something is right or wrong, but it's more about.
Well, I'm trying to also justify this eigenvalue. What is the actual number? What is it that does it represent? Like as an integer, I think it's just counting the number of empty hyperedges, which we don't even render in any way. It's like any hyperedge, any hypergraph can contain an arbitrary amount of empty hyperedges, right? Because they're empty.
Sure.
It's like multiplying by one or something. So.
But what do you mean it represents the number of empty hyperedges?
Maybe in this. What do you mean? Because the number 1 is represented by an empty hyperedge, so the arbitrary eigenvalue like 3 should be represented by 3 empty hyperedges. So this rewriting this
Wait, I don't
eigenproperty
understand that the
somehow
empty hyperedge
introduces.
is represented by number 1?
Well, it kind of makes sense.
Wait, I don't understand that.
An empty hyperedge is like not it's like that doesn't contain any vertices.
Vertices.
Sure.
It's not rendered at all, so it's like a completely empty thing. You can add them as
But if they're empty, couldn't you said you could have an arbitrary number? So how are you counting them? Couldn't you have
well, that's the eigenvalue.
Why would there be a bounded number of these? Couldn't you just have an infinite number of these completely empty edges?
I haven't said it's bounded. I'm saying that this rewriting rule should go somehow should introduce this arbitrary number of empty hyperedges in order to justify the eigenvalue, right?
Okay, but
So
before, but there's two things, right? Because this rewrite rule I wrote completely generically without relation to the spectral problem, right? So this is just one edge, two edge combined to one single edge, right?
Yeah.
So
what would be the scalars? Basically, is the same problem.
Yeah, but I think the scalars, in my view, the scalars represent multiplicity, right? If you want to take a very graphical approach, scalars represent multiplicity.
Yeah.
So
it's just empty hyperedges, right?
Sure, yeah, but I mean, I never said that was wrong. I was just not understanding that if you want to see them formally as empty hyperedges, by all means, right? But
if we have a scalar like lambda, and we want to interpret like.
I see. Sorry. I see where you're. Apologies. I thought you were thinking about the left-hand side all the time. So you were sorry, right? So you're trying to interpret lambda as a in the rewrite context.
Yeah, in the hypergraph rewrite. Sure.
Sorry.
If you have a lambda on the right or anywhere, if you have a scalar, it should be represented by a number of empty hyperedges. That's all I've been saying.
Okay, fine. I mean that's one way to say it, but I don't know if it's too problematic to say. It's probably completely equivalent, but to have like an integer, like some scalar that is just, it carries the units of edges, right? In some sense, so you can times edges with it, right? So it makes sense to, because it's basically a multiplicity, right?
It also carries. It's like in diagrammatic theory, like diagram process theory, those processes or hyperedges with no zero unary. How do you pronounce it? Nowary edges represent dimension. So if your edges have the things that you contract, if your indices have a dimension attached to them, the simple nowary edge represents this dimension number.
Yeah, for sure. No, of course. Yeah. I'm happy to call them like nullary. Yeah, degree zero edges.
Yeah.
Yeah.
So nowary edges should represent some kind of dimensionality. We don't usually have in this context a dimension attached to each index.
No, because these are just graphs, right?
So we have just one always.
Yeah. But you see, I think, but that's the different. I guess. Well, yeah. So you can say that there's only one kind of empty. Right. I see what you meant now. When you said empty hyperedges, you meant several copies of the empty hyperedge, right?
Yeah.
Okay. Yeah. Okay. Now I understand, because I was really getting confused about what you meant by empty. No, but I see your point. Yes, I completely agree. Yeah. I agree with that perspective that you have. Yeah. One empty hyperedge and there's multiplicities of them, like with any other order of hyperedge. I agree with that. Now, and yes, so actually. So this lambda here, then I think it's very clear to interpret. So then of course there's another, so that's a different operation, right? So you have what, lambda floating, it's floating, and you have I, which is, you know, I, that's I. And then this is you just kind of push lambda into the I, and it's just, it kind of distributes over your objects, right? So what you end up with is lambda I between i's. It completely preserves the structure. I mean, I could have put anything. I put I because it's what we have in the formula, but you know, that's the rewrite rule, right?
Yeah. And also, if you think of it, that this lambda introduces this empty hyperregister, you can think of the spectral properties. It's like how many contractions are performed. As soon as you decompose A and X into fully like elementary hypergraphs that being contracted somehow by doing rewriting, it's like how many actual things contracted to a nullary hyperage, how many of those, right?
Can you say that again?
Because the only way to introduce the lambda, right, is to introduce nullary hyperages.
Yeah.
So this operation, so you have to find an X, an eigenvector of this operation of the rewriting rule, should be together with, it's like when we perform our rewriting, we should do the contraction in some ways so that it introduces this nullary hyperages, lambda number of times. Kind of weird.
Yeah, but I mean, another way that I regard, but this is kind of the standard diffusion perspective of the spectrum of a hypergraph, which is to say AX is going like this diagram here shows, right? It kind of moves stuff from J to I in that diagram, right? So the equation is telling you which distributions, right? X, that's the question of eigen, and which distribution and to what degree, you know, what X, what lambda, satisfy this property that they basically only concentrate, right? Because Ix, lambda Ix is basically just growing X, right? It's like X doesn't move. It doesn't flow in the graph. It just grows or diminishes, I guess. Right. So that's, by the way, because we're running out of time, but so that perspective is the one that I think is quite easily generalized to general motifs and to general hypergraphs, and the one that we might actually use, right? And just for everyone to, so what I mean is that these, if you're regarding the spectral problem as some kind of relationship between these rewrite rules, or similarly if you're thinking of it as a diffusion kind of phenomenon, that, you know, you're comparing, you know, just diffuse with your adjacency matrix, or just grow with your sort of self weight or something, lambda, then it's quite easy to generalize to higher order hypergraphs just by considering, you know, higher diffusion, right? So you take several distributions that flow and kind of mix, like hyperages kind of makes them mix, and we can either decide that we do kind of averages of multiplicities, or we just diffuse multiplicities, which actually are sort of non-conservative in some sense. Although a lot of people do, they normalize by degrees and so on to make it kind of conservative or whatever. I think that approach is very doable, and because it kind of only requires the actual, you know, hypergraph writing. So what I'm trying to say is replace this kind of rule for something. So replace this rule for something that looks like. So I'm going to replace the role of A with something that looks like this, right? And then obviously again we have the black and white Technicolor problem, which is that what was previously only one choice, now we have several choices, but it's not to worry, it's just several choices. You could have something maybe that has a distribution in one side and outputs, this will be something more like one-to-many kind of situation, and outputs actually just something here and something here, right? That looks analogous to me. So, how do you actually do that? It might be that it turns out that your ternary edge has to be actually two edges, two edges, a pair of edges. But anyway, the point is that it's quite obviously generalizable, right? Like this is easy to generalize, and so I think the question then, as I said last week or last time, spectra is about random walks, is about diffusion, it's about one-dimensional parsing of a graph, which seems like the entire story because graphs are just made of that. They're just made of one-dimensional edges, so to speak. If we go to higher hypergraphs, we have this much richer set of possibilities, right? Because they can be mixed. They can have order 2, order 3, order 4, whatever. So it's going. I think it's going to be a matter of more like these are the. Let's try to go after one kind of hypergraph or some fairly refined class of hypergraphs, and then do the spectral problem. Like I have this feeling that the spectral problem is not going to be the spectral problem for hypergraphs, period. It's going to be the spectral problem for this class of hypergraphs is this one. The spectral problem for this class of hypergraphs is that one. And to that point, when we talked about this paper where they described this Bhattacharya-Messner product and this AMS note about this ternary general linear group and things like that. In that context, remember that you had a more or less obvious interpretation of a spectral theory. Like there was a strictly, you could interpret spectral theory as the spectral theory of non-commutative rings, right? When your left and right multiplications are distinct. You could actually write it explicitly, and you can show that the generalization of the general linear group in that context was the right thing to do, and so that's the entire kind of thesis of that paper. I think that's the story for that product. I think that's the story for that particular motif, looking at hypergraphs that have that particular adjacency property, right? So if we want something
so you're saying
else,
we choose our motif,
yeah.
and then we define its motif specific spectral.
I think spectral theory is going to be motif specific. I don't see how it would, because I mean it is motif specific in the case that we know, because it does it comes from the motif that you choose, which is matrix multiplication, right?
Maybe this is fortunate. I mean, because it prevents us from having to solve a much broader problem.
Yeah. And that's why, by the way, I wanted to have some preliminary work on just hypergraphs and motifs themselves, and do a bit of classification, a bit of taxonomy, a bit of getting to know the suspects, right? Before we actually commit to any of these and say, oh yeah, let's do this particular one that looks, because I mean, to me, the undirected edges, this kind of rule here, up here, to me, the most natural application of undirected higher order edges are mixes, are kind of chemical. when you want to model something that mix different solutions, right? Because that's what mixes do. I mean, things don't mix in like pairwise ways that they mix two and then the other two. They put everything to a pot and it mixes, right? And the outcome is different. Every node, then it's the result of the mix, right? So maybe as an exercise, I think we should do the taxonomy and getting to know some motifs before we commit to some of them, because we might actually find some that are particularly well adapted for the categories that we want to describe, or SK combinators in particular, or the ones that maybe that have some topological properties, for example, that are manifold like, right? That look like shapes and things like that. But we could also have another criterion, which is let's develop or have a spectral theory based on this idea that instead of diffusing and doing random walks in paths, what these higher order edges, what they do is they mix the weights on the vertices, right? And so I think that makes a well-defined spectral theory. I mean, and I think it could be. I'm thinking live, sorry, but I think that could actually. I mean, it could be an interesting basis for a theory of entropy that, I mean, obviously borrows the fact that you have a spectral theory, so you're going to borrow the general themes from von Neumann entropy that is based on spectra of graphs. But yeah, as far as I can see, that will be the closest analog to actual spectral theory, because actual classical spectral theory of graphs is done normally for undirected graphs, right? So you have the spectral theorem applying for your symmetric real matrices. So I would say that now that I think about it, there might be quite an obvious generalization here. Maybe. Yeah. So just for the record, I don't want to go much longer, but just for the record, what I'm thinking is the following. So if you have, in the binary case, in the usual case, the classical case, diffusion. So spectral theory is defined in these terms of diffusion, where A times X represents that you're gonna. So maybe A is normalized by degrees or something like that, or you're doing the Lagrangian. You're doing the Lagrangian matrix instead of the adjacency matrix or something like that. But regardless of that, what it basically does is it diffuses X as a distribution of masses over your vertices. So diffusion, it's well defined because you're always in one position here and you go there. Now if you have three, the idea is that you want to define something that basically makes this not equal to this. Right? That's what I'm trying to think. So what is not equal? So basically, what I'm thinking is you have some distribution of numbers. Maybe it's more in the number theorist people should. So you have a distribution of numbers, and you want. Yeah, you want to basically do something with these, and send them kind of distributed again. I don't know. I'm thinking live, but.
In that random walk paper that you linked,
yeah,
they define a different transition probability just because they're hyperedges, right? So you still have the same weightings on the vertices, the distribution of weights on the same vertex, but they flow with a different transition probability because it's a hyperedge. So you have kind of higher probability to transition weight from within a single hyperedge than between hyperedges. So the flow would be different for these hypergraphs. if it's within one hyperredge or there are 3 hyperedges.
No, I see that, but was it? I can't remember if it was made by. Was that a definition or was that a consequence of the system? Oh no.
Well, they have some kind of nice justification for the particular definition that they made for this transition probability. I don't remember.
Yeah, I mean, what I'm struggling to think is that this transition looks like effectively matrix multiplication here. Where it's enough when you give x is a distribution, act with a, you get another distribution, right? And it's interpreted as diffusion because it has this additive. I mean, it's this.
Yeah.
You know,
So
linear combination.
Eigen problem would be just a stationary problem. We are looking for distribution that is stationary under this flow in the graph.
Yeah, exactly. Yeah, exactly. Yeah. So, I mean, the problem, I guess, is that, so if you want something that, given a distribution x, gives you another distribution x, well, 2 indices. Yeah, I guess one way is to depart from linearity. As in, you could take something like, I'm just gonna write it in coordinates. So the result y I is a I, and then ijk. So no, sorry, not I here. Let's say something like L, and then aij. Oops. ijk xi xj xk, right? So no. Oh, wait.
And
well, I guess you could just reduce the order by 1. Sorry. So this is k. You can just do it like that. xi xj. Right? And then aijk is the adjacency hypermatrix of an order 3 hypergraph. So this is this is xi, this is xj, this is yk, and this is aijk in the middle.
Mm-hmm. Mm-hmm.
Yeah, actually that makes sense. That's interesting. I never thought of. I mean, it's kind of an obvious choice in this tensor network. If you think about it, it's like you're doing something very standard because it's just a multilinear. It's just a multilinear map between these things. But yeah, I think this is one of the standard ways in which people do spectral theory of these higher tensors, right? Where is this multilinear multilinear approach. But I'm intrigued by the fact that you can so if you had something like you somehow want to contract all these together. But yes, I think this is a possibility. I mean, it is the more standard one, and so perhaps when I thought, yeah, this is an obvious choice, it's a good reality check that this is the one that is actually used in the literature more or less frequently. But yes. Anyway, I'll have to keep thinking about this.
Yes, that's okay. I mean, you presented quite a bit today. There's no need for you to figure this out in real time. You know, you've already been speaking for like 90 minutes.
Yeah.
So
anyway,
we can continue this privately. We can have another live stream for this, but
sure.
We should probably wrap up. Hey, this was a really great lecture, though. I hope that you can put these slides on. You can share these slides with us. They were really helpful.
Yeah, put it on the Discord.
Yeah.
Any other comments, Nick? I'm curious, or Richard? Curious to know if some thoughts or something.
No, for the sake of time, I think not.
Okay. But yeah, we can maybe find some time tomorrow, and we can chat. Like in the morning, in the European morning.
Yeah.
Richard, did you see your mic?
Oh yeah, that'd be good. Yeah, I wanted to go through this and offline and watch through. Then I'll have a few more concrete things to say and ask.
Sure. Yeah, I'll send you a message and we can do one of our already more or less regular Friday.
Cool.
Friday.
Yeah, sounds good. Yeah, I'll be around in the morning.
Perfect. Yep.
Okay, cool. All right. Thank you. Thanks, everyone.
Yeah, I'm gonna
Thanks.
stop sharing in a sec so I can actually stop the stream in time. Can I? Why did it disappear? Okay. So yeah, thanks everyone. Here is a couple of people in the chat. Thanks everyone, and I'll see you around.
Thanks, guys. Yep. See you later.
Thank you, Carlos.
Bye-bye.
Thank you.
Goodbye.